Okay, so during the last lecture, as you not last lecture, but one of the earlier lectures, as you might remember, when we looked into functions, I have shown you this template mechanism that allows you to create a function which does not have defined argument types, but instead can be set up such that when it's being used, the compiler will look up which type you're actually using with this function and then create a particular implementation of this function for that given type. And as I mentioned back then, this mechanism is actually not part of C, but of C++. Back then we were still looking on mostly C only, but for expedience I mentioned that already back then, and then also I said that there is much more you can do with templates in C++, and this is what we'll be doing now. And this is what we will be doing now. So let's create a new project for that. Let's call it templates, and let's take a look how this capabilities work. Create new project, console project, templates, create. Okay, it's creating. So just as a quick reminder, we will recreate a template function, and then we will see what else we can template. And just as a short grab into the future, we can template structures and even entire classes. So we can use this mechanism to implement a huge amount of very helpful helper objects. The whole standard template library STL is based on such templates. We will also take a look on those a bit later. I'm not sure if this will fit into this lecture, if it will be done in the next lecture, but we'll also take a look on that. So let's start with the short reminder how functions work. So we write template, type name, and then we can have some placeholder for the type. Usually you are using just single letters, but you can also use something like my type. What is better really depends on your use case. If you have something simple, then just template T is the standard, and then you just go T, U, V, etc. But as soon as you have more types, or if you are creating something of a higher complexity where the semantics of the usage of whatever you are doing is not doesn't make it clear what this type is supposed to be, since those types can be very complex, it is then recommended to switch to using more descriptive type names. So we'll create a function that returns something of my type, make average, my type asterisk, values, size t count. So my type. First of all, of course, if this is 0, safety check, then return 0. Then my type result equals 0. We here just make the assumption that the type is something that can be assigned 0. So of course integer, double, this will all work fine. If we would create an own class which represents, for example, big integers, as I already mentioned, that's something that is very useful. Usually you would have some constructor which would take integers as arguments to create small versions of them, so this would also work. But if we want to be more generic, we could also use this. For integers, there is a default constructor which is just not used by default, which just initializes it with 0. But for more complex types, this might be the safer approach. So either way, either is good. Okay, then we make a loop for size t is equals 0 and is less than count I plus plus result plus that didn't copy correctly, copy plus equals values at I. Of course, we assume that whatever we will feed here will be just a standard array. We could also use a different approach where we have two defined types, and would be more flexible with regard to the array type. We might generalize this later, but here in this example we'll keep it as is, and then we just return a result divided by the count, as it's customary for taking the average. That is why we needed this test here, since of course division by 0 would not work. And now the nice thing is that with such a template function, as you might remember, we can create whatever we want. For example, int e values 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Oops, that was off by 1. And then we just int e result is equals, oops, it's not typing, int e result that is equals make average this comma. Do we have this defined? No, we don't. We have not included anything that would have it defined, so let's just include Windows H and maybe stdioh as well. Now we have array size, so this is a simple macro which just gives us the element count of arrays which are defined such that the compiler can easily determine the size. As you might remember, the implementation, we did some, okay, it might be more complex. Okay, so here it's not simple, but the simple implementation, if we want to have our own, my array size x would be something like size of x divided by size of x0. So that would be a self-made implementation of the same functionality. It's a bit more straightforward than how Windows defines this nowadays. And the trick with our template function, how to return to this, is that we can define this, for example, as float, and then of course here we need floats, and then everything will be done with float. So basically this this function will get two implementations in the machine code created by our compiler instead of just one, and basically it will get as many implementations as many different types we use with it. And now the fun part begins, other uses of templates. So instead we can, for example, create a structure that is template based. So for example, type def, type name t, struct, my struct, oops, supposed to be my struct, now we can use our team var a, var b, var see, what is this complaining about? Type def, type name t doesn't look like a type anywhere. Sorry, template type name struct, yeah. And then we can have a struct which can have different types. Of course, initializing such a structure is a little bit might be a little bit more complex. So with a normal structure, as you know, you can just start writing something. Here, if you can do it, will depend a bit on your compiler version. Struct is equals 1, 2, 3, and with our compiler version, let's see what we have selected. Probably 2013, 2020 even better. So if we go back enough, at some point here it doesn't like this because it doesn't know which types this is, in which case you just write like this, let's say int, and then it is happy again. So when you use something that is a template, you can use this pointy brackets to provide an argument list where the arguments are the template parameters. And in those template parameters, we can also use default values like with normal arguments for functions. And the nice thing about more modern versions of the C language standard is that it tries often to automatically deduce based on the past arguments what type of template arguments to auto-pick. This is quite useful, especially given that with modern STL you might run into templates which have very complex argument lists. As much as here as can be automatized, the better. And of course there are still use cases where you need to provide this explicitly. So if we would, for example, want to assign this separately, like we define it somewhere and somewhere else we assign values, then of course here it cannot know the type since there is nothing to observe immediately. So then we still need to provide what type we expect. So we could create my ice struct, ice struct. Damn it. No, it's correct. And my double my destruct, and we can initialize one way and the other way, so that we see both use both cases here as an example. And then of course we can create a function which will also take a such a structure as an argument. So what do we want as a return argument? Let's go with int, or let's go with something more complex. Let's go with template type name t and u, and we'll do the return type my struct sum. It will just sum up all the parameters in the struct. It will take one argument of type u val, and it will take an argument of type t, which will be our structure val, sval, like for structure value. And as a return parameter, we just want to, let's say, return val, and to val we want to plus equals everything that's defined here. Obviously, when we use a dot operator, or if this would be a pointer, if we would use an arrow operator, it cannot tell us what is available because it doesn't know that. And now we can just write our known members, and of course then this function will only work for types where these particular members are defined. So for example, we could make my struct I with integers, and we can use the other one for other things. So we can feed this function either just this struct with whatever template is compatible, or we could feed it this struct. It would in both cases be happy with that. But as said, the member functions, the member variables, I mean, must be of course consistent, otherwise it will not work as expected. So let's use this function, and we will rely on the compiler here to find out the right types. Let's call it I red, my sum 1 2 3 comma this, and as you see it is perfectly happy. We can do the same thing with the integer struct. It will be also happy, and it will create, as you can see here, it shows us what is fed into it. So you see this my struct, it uses a my struct of double as a return argument. It uses int, while here it will be using int for everything. We could also, for example, here make this my I struct. Then it will also be happy. We just see when we look on the preview that now it uses the simpler I struct structure. The compiler is not complaining, and I realize we haven't run anything, so let's run it just so we see that it really compiles flawlessly. One thing that where one needs to be careful with regard to templates is that unlike normal code, the compiler with regard to templates, while is able to some extent make guesses about what is correct or not, so basic syntax error will always be complained. But for example, if we would add here something that just makes no sense in the context, we'll later use it. As you see, the compiler is not complaining because it doesn't know yet, or rather the IDE is not complaining. The compiler will, because the compiler will then have to actually do it, and then it will find that here var d is not defined. But we will not see this nice red underscore, like if we would just somehow scrub the syntax. Although sometimes even if you just scrub the syntax, it will still not complain. Only once you try to compile it, it will complain. This is a bit annoying because you write your template, it looks okay, and then you start compiling it, and then it throws errors and errors, and you fix them, and it throws even more errors. So it's a bit as the programming experience was before the IDEs became so smart that they highlight syntax errors and such things in on their own. So it's not a big problem, it's just something to be aware of. And of course, now, as we have seen, we can use function, we can use structs, but the most interesting use case, of course, are classes, because this really makes the whole thing powerful. Of course, in C++, a struct and a class are very similar, as I already mentioned in the last lecture. But if we look from C to C++, the difference is significant. And of course, when using own classes, then one you can have all your types that are templates. You can have functions that do different things, so you can create very flexible objects that can do great many things. So here, as an example, we could, for example, implement an own smart pointer. As you might remember from many of our lectures, memory management is something to be very careful about, and generally using raw pointers is error prone, and if something goes wrong, it can go very wrong. So obviously one would want, in modern code, where you don't need to squeeze out every single bit of performance, but rather securities and such considerations, maintainability, etc., are more important there. It is very recommended to use container types for at least pointers and arrays and strings and such, so that you never need to do raw memory operations yourself. That helps a lot. So let's here see how such a very simple smart pointer could be implemented in a nice and elegant way using templates. So template, type name t, and type name d. So the t will be the type which we are holding, which the pointer will point to, and d will be a deleter, so something that will then perform the memory release operation once the last instance of this pointer gets out of scope. One could, of course, assume a certain behavior. So we could assume that we always create with new, and then we would just use the delete keyword. That would be a reasonable approach in many cases. But if we want more flexibility, such that we can also use custom heap allocs or a custom memory allocator entirely, then of course it is nicer to be able to use some custom delete function. Plus, this will allow us to demonstrate another nice property of C++, so-called lambda functions. So, but before I tell you what this is, let's continue with our smart pointer. So it's a class. Let's call it CMyPTR, so CMyPointer. Zack. We need most things to be public. We will need some things to be protected, and we will protected typo. And we will want some things to even be just private, because we will want to prevent certain things that normally C++ implements for you completely opaquely, we want to explicitly disable them for this particular use case. So let's start with our protected things. So we want type asterisk, my PTR, or just mptr. Let's put that like this. So this will hold our value, and I'm thinking what is more elegant. For now, let's just not do any default initializations. We just go with this, and then we will have a function pointer d delete. Let's call it mdel for delete, which will then point to a function which will be doing the deleting. So this will be the thing that gives us the total flexibility. Okay. So now, of course, we need to assign these values. So we will create a constructor which takes const t asterisk ptr, comma d del, and then let's initialize the values del from del, and for the other one we can use a different initialization method. Mptr is equals t asterisk. We want here to strip the const property, ptr, and then of course we'll have our destructor. So this will be called whenever we leave the function, as you might remember from our last lecture. Whenever we have something that is defined on the, well, it not just on the stack but also on the heap, but generally whenever, the important use case here is that we would define such pointers only on the stack, and as soon as those go out of scope, the generated code automatically invokes the destructor. So we have here a automated time of life tracking for our objects. This is what makes this smart pointer so useful. So here, if the destructor gets called, we can just delete our ptr. This type of pointer is of course a very basic, because it does not support any sort of shared access. So we can create an object, some memory object, and put it into this pointer, but we cannot really copy it to another pointer to have a more advanced lifetime management. So the smart pointers that STL uses are of course much more advanced. There you can assign values of one pointer to another, and then so you can have multiple pointers pointing to the same memory, and the system will internally keep track and only free the memory once the last pointer gets out of scope. While here we don't have this mechanism, we just delete as soon as our pointer gets out of scope. So in this way our pointer is a little bit dangerous. So what we will want to do is we will want to ensure that once we created such a pointer, we are not able to create a second pointer and then assign its value, because this would bring us into the aforementioned situation where we are missing the right lifetime tracking. So what we can do is we can remove certain functions which would automatically be created by the compiler for us. This is the copy constructor. Reference. So it's a constructor which is basically used when you are just creating an instance of a given type, and then you want to in the same line assign it already some initial value. So it takes another copy of the object and assigns it. We can then just write it like this, which will tell the compiler that we want this thing to be gone. And the other thing that behaves similarly is the assignment operator. So equals takes the same argument here. We want this to be gone as well. So as you might remember, we can easily, let's quickly open this. The old project we had opened in the last lecture. What was it? Did I forget to show you how operators work during the wait, this is not the right thing. Classes. I just opened one file, sorry. File. This one is the right one. Classes. yeah, so as you might remember, we have here this I showed this addition operator, and of course you could also create an assignment operator or any other sort of operator that is normally defined for normal built-in types. So one of those operators is also this assignment operator. And it is in this case for us important so that we can overwrite it, that it will not be created. Other operators like for example plus, they are not auto-generated because the compiler cannot really on its own know the syntax and what are the semantics, I mean what we would want our operator to do and how we would want it to behave. But for the assignment this is quite easily just deducible, because we, in the simplest case, we just want to copy the memory block and overwrite it with the other memory block. So this is something that the compiler assumes if we don't specify our own, then it will do this instead directly. So let's go back here. So we have here this disabled so that it will not be created, and now what we need are a few functions how to access the contents of our smart pointer. But before we implement those, let's quickly start using our smart pointer already, since we have the basic necessities. We can use it. We will create a scope so that we can test the simple mechanism where it gets rid of itself of the content. So see my PTR, let's call it handle, and let's assign something to it. For example, want to be a array of integers, heap alloc, or let's make it simpler. We just make new int 10, and then we need the deleter, so we will be using a lambda function. So like this, int ptr. So with the lambda function we start with a captcha list. So here we could specify which variables from the existing scope we want to be able to access within this function. Then we have the arguments for this function. And if we use an empty captcha list, this is quite simple because it's more or less analogous to just write a function here and then just put it here as a pointer to it. But with the way this works in modern C++ is that you can also create this captcha list, which is quite convenient because we can then pass other parameters. I will make a more complex example shortly. And here inside this we just delete our PTR, and then we can already test this. So the creation of course is kind of not interesting, but we can see how it behaves when we are closing the scope. So step by step we jump into our destructor, and our created variable, our memory, will be freed by invoking the delete operation inside of our lambda function, and then we exit everything. So this is kind of the whole idea. But now of course we would want to somehow use the values. So for example, we'll just assign values 0 through 10, int e equals e is less than 10, e plus plus. Of course here doing this is still risky because we don't know where the limit is, so we could still run into troubles. But as you see, at least we would not leave the memory undeallocated. So as you see here, it complains because it doesn't know what to do. So we need to create a square bracket operator, and we want t reference to be what it returns. square brackets size t index, and this will then just return asterisk ptre. T will be small, and of course here we could have at least add some sort of safeguard that, for example, we could bug out if ptr is null. That would be one simple safeguard we could add. What we also need is another operator that works in the const case. If it looks the same, it just returns a different type. And then we might of course want some means to access the raw pointer inside. So we have the function ptr, which just returns. And for completeness, we also need to add the reference operator. We could add reference, which just returns pointer, and in the same case in const t. And last but not least, we should add the error operator. So the error operator returns t asterisk. This is not quite right. This needs to be yeah, like this. So if we would, for example, do something else, let's comment this. So here you already see this is no longer complaining, but let's create something else. For example, my pay my struct, and then we want to make this, for example, and then this would need to have the type, and then we can have delete. Yeah. So now with pay struct, we can use the error operator to access the ABC variables and member variables on our structure without having defined the error operator. This would not work. So if we don't have the error operator, we cannot use it, obviously. So this is quite useful, that we can really replace any, maybe not any, but most parts of the basic C++ mechanics with our own objects and our own operators, such that we could use this smart pointer as a more or less drop-in replacement for a normal pointer. There are, of course, various considerations when doing such things. For example, with regard to the size of the object, since if we have a struct here and it has two members, then obviously this will no longer fit into a register. So if we have functions which took normal pointers and then we change them to use our smart pointers, this will change how these functions look in the code quite significantly. But for us, as long as we don't need to maintain binary compatibility, this would already be good enough, as it would give us at least full API compatibility. So on the code side, we have the full compatibility. We just need to recompile the project and everything will be working when we change the types from normal pointer to such a smart pointer. What we lose is the API, so the binary compatibility, meaning that if we would have some library or such already compiled and we would load it and try to use functions, then of course this would no longer work, since those functions which would expect different ways of passing of arguments, and of course internally would also not know what to do with such a pointer. So while it says this is a nice drop-in replacement, there are edge cases where it does not work quite as perfect. And now, as I said, let's also take a look on a more complex case here with those handle. So, for example, we can create another my heap handle, and then we'll here oops create an own heap. You don't need to make it do anything particular. We want to maintain the right type. Let's call this h for handle, and then of course this is not delete, but oops. The syntax was heap destroy. Heap destroy from and h. So this thing will create an own heap instead of using the application. The default application heap will have our own, and once this goes out of scope, it will destroy the heap. And you will change this to use heap alloc. So int asterisk heap alloc handle. Actually, we could maybe simplify this. I don't think we need this to be something different. Let's go by this. So is this return a handle? Yeah, this already returns a handle, so we don't need this either. So we have our heap alloc. It takes our heap handle punct ptr comma because we need to kind of get the handle out of it, because this API doesn't take a smart pointer. So this we could also use the add operator, but this is not something that most smart pointers implement, because it kind of is kind of wrong, because an add on a handle, you would rather want to not get the internal value but just a pointer to this handle itself. So maybe because this is kind of not quite often correct, it's just something that's quite convenient, we should comment this out and only stick to the known okay-ish implementations. What we could of course also add would be an operator like what was the syntax? T asterisk T asterisk, I think, that one, and ptr. Oops. And then we need of course the const version of this. So this is something that is semantically valid but dangerous. So here, this way, we could just keep it like this, and it will accept it. And in this case, the compiler will, while it sees that this thing takes just t asterisk, it will invoke this. Why is this not happy? It should be happy before. So it would then automatically invoke this function to do this conversion for us. But the thing is that usually when you have smart pointers, you would want to not be able to just write, let's see, in this case, what we had in. So for example, like int asterisk is equal int asterisk, my variable name is equals this smart pointer variable. You would want this to somehow not work, or give you a warning at least, so that you will not accidentally convert a smart pointer to a normal non-smart pointer, since then there are other things you need to keep in mind with regard to the lifetime. So ideally you would want to create an object in a smart pointer and then keep it in a smart pointer forever. And if you want to make an exception to that, then what you would do is you would have some function which you then explicitly call, that makes you explicitly think about that now you are kind of accessing the inner object and need to think about the lifetime. Because if you would have here, for example, some function that takes the pointer and then keeps it, then of course this would be much more problematic than a function which takes the pointer and only refers to it as long as it runs, and when it's done, the pointer is then again fully owned by the smart pointer mechanism. Okay, so let's continue. So 0 as flag, Caesar of int times 10. The destructor remains the same, but of course not delete, but here we then would use heap free, and then we somehow need to pass this handle. This will of course as is here not work. 0 ptr, but we can make it work using this captcha list. We can either use just add, which will just capture in the list everything that is available in the scope. So it's a workable option, but not an elegant one, and depending on how you are using your scope, you might run into lifetime problems of other objects. So generally I would not recommend to just use such a blatant catch-all sort of approach, but instead we can explicitly specify what we want in our capture list to be captured. And as you have seen here, for example, now like this, it means that we want to capture it by value, so make an own copy, so that we are not longer reliant on this object remaining alive, but we have an own object. But here we cannot do this because we have disabled the copy and the constructor. As you see here, it says that it is inaccessible because we put it here in private, so no one can use it even if they would want to. But what we can do is we can capture this by reference, meaning of course that this thing needs to stay around, and we cannot get rid of it. But here of course the way we did it, the stack will be unrolled in reverse order, so it will first do the destructor for this and then the destructor for that. So that should be just fine. Let's run it. Something is not quite right. We broke something too much. So quick test step by step. Interesting. What did I break? This should normally work with handle. Let's quickly see if how much did I break by uncommenting the other demo case. And this of course here not quite right. Oh, that cannot work. That was a typo. We apparently never tested the other use case. We just saw that it does not complain, and now it's fine. Right, so let's return to our more complex example. Technically, let's go. Okay. We don't need to just go with print warnings. Where would it save? That's why I did it. Handle. When we create our thing here, the type handle as such is defined as void asterisk, and this thing here, void reference, is not a valid thing. So we in fact need to somehow not use handle type as such. So we can for our create heap go with uint ptr asterisk or just uint ptr, and then we just have this, and then I think this will not like, we will need to use two conversions. Let's go like this. Yeah, now it should be happy. It's not as pretty of a code, we forgot the breakpoint, but it is functional. So we have here of course our handle that contains the thing where we have written where's the address, memory 1, our 1 2 3 4 5 6 1 2 3 4 5 6 7 8 and so on, and 9 and 0 into, and then of course the destructor. Then when we proceed, we see that we first end up in the destructor. Well, actually it's a template, so we don't really know which one it is. It looks more or less the same for both cases. We can see here, based on the call stack, the call stack displays us for the template function all the arguments with which this was created. So here we see that this is a pointer that uses int as an internal value, and then a lambda function in main. So this is, and of course as we progress here we will end up in our delete function, which is the lambda, and then we are done with this, we are done with that, and then when we keep going we will end up in the other one, which now has a different type, unsigned int64, and another lambda, in this case the one that does the heap destruction. So the order is maintained and everything works as expected, and then of course voila, we are done. So we could of course create also an own array and add to it much more complexity, like the ability to detect out of bounds accesses, another variable that keeps the element count, for example, that would be needed for this, and so on. So as you see, we can with templates more or less redefine everything to fit our needs. And since we did not use all the interesting operations here on the classes, we can maybe extend our pointer to be a real smart pointer, so you can add to it the ability to be reassignable and so on. So let's do that quickly, though it will not be that quick, I guess. Let's call this then my because the other one will be like really the smart point, or let's call the other one smart point, and this will just remain pointer. That is, I think, a reasonable approach. So we don't want this, we don't want that. This we will want, but public now, and of course not longer overwritten. So this goes here and that goes there. I think they will need a body. So, and we need a name, so my smart pointer. Of course we need to do some renamings here. Okay. This for now we can actually we could leave this as is. We just put this into individual sample scopes. Then those different examples will not interfere with each other. I mean, even in the same scope, the only conflict would be the name. Right, and then we'll make here a scope where we'll test our smart pointer. So, right, so this stays as is. We could even define here as an additional demonstration a default destructor. So let's do that later. For now, let's focus on the smart parts. And the most important thing in the smart pointer is that it will need to have some sort of shared state tracking, and this is what also makes this smart pointer a bit more complicated, because by using it we are effectively creating yet another object. There are ways around this. If you want your smart pointer only to work for certain classes, not be just a generic works with everything sort of object, then you could make it just define it in your own program that all types the smart pointer is supposed to work with have to provide a member for reference counting themselves. But here we want to go with the more generic approach, so we will create this object ourselves. So stoked, let's call it S smart PTR and just call it M. So this structure will hold all that is relevant: pointer, the deleter, and a reference count. Long ref. We should initialize this with null ptr. Okay, and we will then need some things, some protected things to work with this. Let's do it here. So we will need a returns us this thingy. Although we could do this on an as needed basis, but for now let's keep this here. This will just create a new. Actually, let's make it differently. Let's initialize everything with. We initialize everything here ourselves. Then we need one less function. So then what we need will be a void attach, which takes a smart pointer p, let's call it. Then we need a detach. That doesn't take anything. Detach. And I will quickly implement this, and then or maybe I'll explain what the idea is. The idea is that when we are assigning or copying the instance of our pointer, we will be always invoking this attach function, because the idea is that then our object will attach to an already existing smart pointer structure, which has been created by the first smart pointer which we have created to point to something. And then whenever this attach happens, this reference count will be incremented by 1. And this detach we always will call from the destructor. We can do that already. Also, it will be always auto-called from attach, since we might be in a situation where we are assigning to an existing smart pointer that holds a value at the value of another smart pointer, and this one smart pointer, of course, first needs to detach from what it was connected to, and then only then it can attach the new value. It might also happen that it will try to attach, and then it will see that p is null if we are assigning an empty smart pointer to a non-empty smart pointer. So if this is not, then just return, because nothing to do. And of course here in detach, if m is not nothing, then also there is nothing to do, return. And the idea is that detach will decrement the reference count in a way which is thread safe. I will explain what it means in a second. And then it will, if it sees that ref count is 0, then it knows, aha, now it's my responsibility to delete this memory, to free it, to invoke our delete operation. And the important thing about such smart pointers is that you want them, usually at least, to be thread safe, meaning that if you are running multiple threads in your program, and each thread is doing, well, something, then while they are running and doing their things independently, that you can have a pointer in one thread and another smart pointer in another thread running on 2 CPU cores simultaneously, accessing these pointers, that they will not maneuver your code into some sort of inconsistent state. For example, as I said, we decrement the pointer and then we see if it is 0. These are, as it sounds, 2 operations. Thus, if both threads at the same time would say we now detach, both would decrement by 1. Then, for example, and then would both check what is the value of the value. So initially it was obviously 2, since we had 2 pointers. Both did a -1, then both see it's 0, and then both will try to delete your memory. And this is of course not valid. We are not allowed to delete memory twice, or free memory twice. We are not allowed to delete an object twice, would be the more correct way to say it. So we need a mechanism that will prevent this from being able to happen. We need some sort of synchronization between those 2 independently running threads that will ensure that in the end one will have seen that there was still one pointer left and just does nothing, and the other sees, okay, I'm the last one, there was nothing to do, I can delete it. And obviously this, since you are using this as a replacement for a normal pointer, should be an operation which is very efficient, and various synchronization mechanisms in an operating system are not very efficient. They require context switches to the kernel and back, and a lot of operations. So you would ideally try to implement such a atomic reference counter using the CPU's own capabilities, so that you don't need to ask the operating system mediate this access for us, so that it ends up okay. But instead you would want to just tell this to the CPU, and then the CPU can do it more or less at minimal cost. And modern CPUs contain functions, special opcodes, which are made to achieve exactly this. and they are called atomic operations. And the idea is that usually such an operation is a complex operation. This is made up of 2 or more steps, but the way the CPU internally will manage memory and cache line ownership will ensure that the memory that is being worked on will be released for the next multi-step operation only once this operation is fully completed. Sometimes you might also find definitions that they say that it's guaranteed that it will either succeed in one step or fail, but this is not very useful, and usually nowadays all the typical opcodes that are used just one succeeds and the other waits and then also succeeds after it is allowed to. So we will use such a mechanism here. We have defined already a variable for that, but one thing after the other. So let's first continue with our implementation. So we already have here our destructor. Here we have our constructor. So here we will want to create a new m. M is equals new. So of course, one obvious downside of our approach is that whenever we use such a pointer, we are also using unfortunately at least one additional memory allocation or deallocation. So there is some performance penalty which has to be paid if using smart pointers, but usually this is acceptable, and the advantage in security and convenience outweighs potential downsides. So we create a new m, and we just assign m arrow ptr is ptr, m del is del, and then we attach m. As you might remember, since we have pre-initialized this with 0, more or less once this line is being executed, we will jump to this and set it to 0. So attach will here call detach. Detach will just do nothing, and well, attach does its thing. We could, of course, here, since we know that this thing does nowhere exists, we could set ref equals 1, and of course that is not quite right. We should use a temporary variable for that if we want to do this correctly, because m will be assigned by a p. So this thing here, it checks that m exists. Attach checks that p exists, and if p exists, then it will say m is equals p, and it will need to increment the reference count. So interlocked add long. Oh, did we have the right type? No, not right. It should be just L. Interlocked add reference p ref p. Okay, is correct, but why doesn't it say ref? Well, just write by hand. Ref, comma, and we just add 1. So this is quite simple. We just increment by 1, and the thing about incrementing is you might think, well, if 2 threads run in parallel, incrementing is easy, but given cache behavior, you might have a situation where you start, let's say, with a value being 1, and then 2 threads try to increment this value to 2, and you might, what you expect is to get the value 3, but you can have a situation where each creates like some sort of local copy, or it's just cached by multiple CPU cores on different dice in different caches. Then it makes it 2, and then it writes the cache back, and then it writes back the value 2, even though the expected value would be 3. Here, the interlocked operation ensures that the cache ownership in the CPU is set such that you cannot have such a parallel thing happening. One will do everything, then it will write the cache to RAM, then the other core can grab the cache line from the RAM and do its own incrementing, ensuring proper ordering and that everything will be executed correctly, and you will get the expected result. So attach, as you see, is quite simple. Now, of course, we want to implement the detach. So we already know that m exists. So now what we do is we will have an if interlocked let's see, which do we have to I think in interlocked we should be able to just use interlocked add as well. Let's just quickly see. the semantics of this. The idea generally is that those functions return you either the current value uh, or the last value, and for this one does not return a value. Look at let's see, what else we have available? And could use interlock decrement. That sounds like it does what we want. Yeah, that's better. So let's here also use interlocked increment. Oops. Increment. This will there we don't even need to specify plus one, the value. Just go with reference p f. That's why it doesn't look. We were missing the semicolon. That's why it did not suggest us ref. Now it should. Yeah, now ref is here. Right. So here we make interlocked decrement. As you see, there are also a 64 and 16-bit versions, so we don't need to use a long, but usually a long is reasonable. And this function returns the result of the operation. So we just check if this is 0, and if it is 0, we know that we can free it. And then of course, so this should not be p, that should be m. And then of course, in any case, we will set m to null, because we are disconnecting. So if this is 0, and the nice thing is that even if two threads run in parallel, both try to execute their decrement, one will see as a result 1, and only the other one will see as a result 0. So we always get with one operation seeing to be the last one, thus it can safely call m delete on m ptr and then delete m itself. Okay, I think we did not forget anything, at least for the very simplest of demo cases. So let's just grab this test case here and use our smart pointer, my smart ptr. We don't need to change anything. I said the way this mechanism works is it is quite a nice drop-in replacement. Well, so I said this will just work. We did not implement anything new yet. We can run it and quickly. We don't need this breakpoint. Let's keep this breakpoint and one here and one there. Right, I didn't edit the other code, so it's of course not happy with this. So let's keep implementing this part. So here we just can replace m with mptr like this. Okay. We have forgot one thing. Oops. M. Alright, wait. Isn't m an error? Oh, we wanted m to be a pointer. I forgot to add an asterisk here. Now it's closer to being fine. ptr const. Right, we had here the code that we don't want const, just want t, that I forgot to copy. And lambda function. This is of course not great. Let's do it like this. So we cannot assign null to a complex lambda function. If we would have a simple lambda function, which basically is just a function pointer, that would work. But since here we might also use more complicated lambda functions, we want here this way of initializing it to a non-operation. Right, so now we of course went a bit too far, so let's run it again and step into the code. So what happens? So we end up here, we assign our initial value, then we create our new pointer, and then we attach. For this we first detach, which doesn't do anything since we don't have anything attached. Then we see that there is something to actually attach, and then we are complete with this operation. Then we go to the next breakpoint, which we remove, since otherwise we would end up 10 times in it. Here, as you see it, is as before, it's very trivial. And of course, the destructor just makes detach. Detach checks whether there is something to detach. It makes a decrement. It has seen it's the last one. It frees the thing by calling its appropriate lambda function, and then it deletes our m, and then it sets m to null, of course, to get a defined state. And now, of course, the funny things we would want to put this in yet another scope. Put this my outer handle, let's call it. But we don't want to initialize it with nothing. We just go with null ptr, so this is empty. But the thing now doesn't know what it is supposed to be, so we could say int asterisk null ptr, or we could say but then it would kind of expect the second argument, so now we would need to provide a lambda function, which is kind of annoying. So it's much more convenient to just go with this approach. Or of course, if our smart pointer would not be that flexible, and we would just use a default argument here, which we can add later, by the way. This would also be more convenient, but this way is also fine. It just looks a bit odd. And now what we will do is here we will assign our outer pointer to our inner handle to our outer handle, and it doesn't want us to do that because we did not implement the assignment operator yet. We'll do this in a second, and here let's say printf %d space. Oops, this should be of course like this. And here we just will print the thing. Okay. Why is this not happy with handle? Right, handle doesn't exist. We need to use outer handle. And of course now the missing assignment operator. But we already have this. Wait, smart pointer, out handle. I think the assignment operator is just not quite. It should be correct. Const smart pointer other. We do not have other assignment operators that would be a problem. Anyhow, let's quickly implement it. So this thing would just call attach of other.m. And here this thingy, and then this constructor would also just do attach of other. Now let's see what it is not happy with. Let's just compile it. It sometimes gives us better error messages. It does not like our lambda function. Because we could have in principle used the lambda function here, which would capture something local, and then this would not be available outside. So it does not allow us to do this, even though we are not capturing anything. As those functions look the same, we could I mean, for simplicity just of the demonstration, we could make this pointer just operate on a predefined delete operator, so that we don't have a lambda function at all. That will simplify things considerably. So here we just get rid of our d, and here as well. Del does no longer exist, and then of course here instead of del we will just call delete a ptr. So in this case we are then committed to one particular a deleter, but other than that, that should be fine. I think we forgot to remove one thing. Okay, doesn't want to jump there. This needs to go, of course, then as well. Right. And we don't have a default constructor, so let's say null pt. We should actually add a default constructor which does not take any arguments, because this is more elegant. Although here, I mean, we could reuse this one, because in principle we should check whether this actually exists. Because if it doesn't exist, then we can just return. Depending on how we are using our smart pointer, we might want to assign something where we don't know whether it will create an object or not. And then, of course, if it doesn't create an object, we don't need to make this somehow keep track of something that's null anyways. Why is this still not happy? That's why it's not happy, because to it this content looks differently. It might have worked even with the lambda. Let's change this. Let's change this back and try a different fix. Right, but this we still of course need to we still complain about it. Let's fix it one by one. So there are a few things which needs to be changed. First of all, we always need a default constructor, in this case at least. And here the thing is that this doesn't look to it as it should. Int asterisk. Now it looks it should look fine. Int asterisk. That should be. Oh, that should be just int. Now it's fine. That was the root of the other assignment error. But this, now it's fine. Good. Okay, so this is now complete. Let's run it. Almost. Right, we forgot to return here something. Return reference. Return this. Oops. I add return this. Okay, now it should be happy. Right, so let's go step by step. So we have created those 2 pointers. We have assigned some initial values to the object inside the pointers. Now we can do the assignment operation. So it just goes to attach. It will do detach, which doesn't do anything since there is nothing to detach. Then it will increment our reference counter, so now it's 2, and then it will assign the thing. And then once we're out of this, we are out of scope, which triggers the destructor, which triggers detach, which sees that there is something to do. It dereferences by 1, but it sees that there is nothing else to do, so here it then just sets null. It is done. Then here we will be able to use it. So let's quickly see that it prints the right numbers. Yes, and then in the other case we again do detach, but this time it knows that it has something to do, and then it will do it. So that this much to this. And as you see, now our smart pointer is quite capable, because we could do, of course, even more complex things. So we could have a function called void init let's call it test init, which would take a pointer of this type. We should call it not handlebar, just pointer ptr. Then it will do our initialization. Suck. And then we can of course make another one that does the printing. Let's rename this to pointer everywhere. Okay. We could have like also a function which deletes it. Now in this case, the way this operates internally is a bit inefficient because it creates yet another instance of the pointer, it does something with it, and then it dereferences it. It is not very wasteful since everything here happens on the stack, but a small optimization could be, for example, to say that we have a const reference pointer here, because now we can pass the thing in a register, but now it's of course complaining that it's const because our const returns const. If we would make this not here, not const, then we could do the assignment here. So how we define our smart pointer is of course important, but here, since we want to exercise this mechanism, let's leave it like this. The additional complexity of calling this through the stack is not that significant, so it is efficient enough. Yeah, we can just run it, but obviously this will just work. There is nothing to expect that will would break the behavior of our thing. We can of course now try to also re-add the custom delete mechanism. Let's quickly do that. But this time let's actually think what we are doing. So and let's also add a default delete implementation. So generally, since those things here are types, we need something that's a type. For example, a struct default delete, or let's call it as delete, which will get a function with a capital D. This thing though needs to be a also a template. So template T, template S, delete T asterisk ptr, delete ptr, and this must be static. Okay, struct needs to be terminated. So we can here write this. Of course, not quite. It needs to know the type. T asterisk ptr. T here was, it should be fine. Void is missing. In the return type, of course, and then here, once we want to delete, we will use our now wait, we want the static, we don't need the this of course complicates things a bit. This complicates things because now of course we would need to always use this type and create an own deleter type, not longer use a lambda function, but I guess this is good enough. So let's go with our deleter. So we have our D here, and instead of delete ptr, we call D delete ptr. This also saves us a little bit of memory, since this will then only be compiled and created as code and not instantiated for every object. And first of all, the thing still here is happy because the delete, let's see it, has a default value. So when we go here, it was the wrong breakpoint to break. This one is the one that will go into the delete, and then we end up here into the delete. So as you see, that works fine. And now if you would have, of course, here not new, but well, something different, like malloc size of int times 10 int asterisk, we would of course what's missing here? Yeah, we will need to, that should be fine. Ah yes, one bracket was missing. Now of course this is not quite good because this thing here would still use the default deleter, so we will need to create a new one. struct my delete well, int asterisk free, and then we will use our own delete here as an argument. And now this is of course no longer compatible with our test function, so we would need to, we could make this function just a template itself, then it would be happy with everything. Let's do that. It's the easiest thing. Type p pointer, yeah, and voila. So as you see, when you start working with templates, you might create more and more templates of more and more things. So this can get complicated fast. And another thing to consider is that you could of course create a more complex mechanism here with a derived internal object, so that you can have a generic function which does not care for the deleter, only cares, for example, for the type. But this would make things even more complicated, and I think we should not overcomplicate things unnecessarily. So this is, I think, a quite verbose example of using templates. And one thing you might have noticed is that we have been only using a C file. Of course, we could put the templates into a header file, but it's important to note that normally when you create templates, you would not create a CPP file for them, because inside the CPP file the compiler wouldn't see what to actually do, which types to implement. So if you have some sort of template class, everything you do is in a header file, and thus it might be a little bit unelegant. So in such cases you might want to maybe create some generic helpers which you can put in a C file, which would not be type dependent, depending on the complexity of your class. Of course, this might or might not be possible. For example, for our pointer or for many other simple types, this would not be practical, because basically everything you are doing is type related, so you don't have the freedom to have some functionality which is the same for all of them. Alternatively, what you can do if you want to use a CPP file and you want to and you know which types you will need, you can use a type dev to specialize your template for the necessary types inside the CPP file. Then the compiler will see and know which specializations to implement, and then it will also work. But this is quite unelegant, so I would rather not do that. It's okay to have a large header file, especially given the nature of the typical functions that you will implement, the typical classes you would implement as templates. So what you also can do, which I haven't shown here, is you could have a normal class and have just one function on the class being a template. So the rest of the class can stay in your CPP file, and this one function, which is a template, would then be just implemented in the header. And as you have seen from our last lecture, it's perfectly fine to implement at least short functions inside the header. In principle, you could also implement very long ones. It's just a question of code readability for the user, whether you do it or not. Are there any questions? No questions? Okay. So if there are no questions, then we can continue with the next C++ feature, which is quite important, which also combines quite nicely with our scopes here. That will be exception handling. So let's create a new project for that. We could reuse this window here. New project solution. Yeah. Exceptions. Don't save. Okay. So the idea with exceptions is that if something goes wrong in your application, you can abort the execution wherever you are right now and return to a defined state. In in normal C, there is also a mechanism to handle exceptions, but it is much more limited in scope of what you can and cannot do. So a typical example of an exception would be, for example, if you divide by 0 an integer value, then this causes a hardware fault, and the CPU triggers an exception on its own. Also, memory protection failures can also trigger exception handling. So, for example, if you would want to access an invalid address and write or read from it, you would get a memory access exception. But generally, the amount of exceptions which are available in C are rather limited. They are just your typical hardware exceptions. There are certain means how you can trigger more custom exceptions with the help of the operating system, but this is not uh, that much a CPU feature then anymore. With C++, the whole thing gets significantly more complex because in fact you can trigger very complex arbitrary exceptions on demand, and let's see how this behaves. So before we maybe take a look into how C++ works, just for completeness, let's take a look how this works in just C. So if we want to somehow handle exceptions, we start this exception handling with a try block. And inside this block we write something that will do something. For example, we'll call a function called test, which we need to implement. Void test, let's include some std and f. Test. And when we are done with test, exit test, and inside we will do something that is not okay. Let's say we want to divide by 0. We will make a function that does this for us. Void divide by 0. Oops. Divide by 0. So int x gleich 1, int epsilon gleich 0, and int z gleich x divided by epsilon. So this will crash, and when it crashes, we will see what happens. So about this, we have this, and of course this try thing is not yet completed. We need to add a except statement. Now rather than except block, oops, not capital. And the thing has a body, and it has here a short thing where you can add some more code. And what you add here is you either just set a value you want, how you want this exception thing to behave. We, by the way, need to include another thing here, except H, and I think this needs Windows H. That's not written correctly, except H. Windows H we might need later anyways. And there are values that you can use here. So for example, exception execute hand, oops, the handler exception execute handler. Okay, they are defined here, so you have those three values available: execute handler, continue search, or continue execute. Execute handler means just do whatever is here. So we can here, for example, write another printf. Inside the exception handler in main \n and semicolon. The other values, continue search means this block doesn't feel responsible, someone else should handle it. And continue execution, that's something which is very important, but for us as not operating system writers, rather useless. It just means just try again. So basically retry this and retry this. And if you just do it, you retry this 100 times, it will never give you a different result, because divide by 0 is divide by 0. It only is useful if you can somehow mitigate the error. So for example, if you would know that this might happen and know the address of x and of y, and then overwrite y in memory, and then say it to retry it. But that's obviously a extremely dirty hack and usually not something you would want to do. Where this is useful is, for example, if it's a page fault because a memory was paged out, but it still exists on disk. So then the operating system can catch this, see, aha, this is a memory access exception, but the memory page for which this happened is marked that this data is now on disk, so I will read the data into a new memory region, map the new memory region into this memory range for that page, and then I can tell the CPU to retry the operation as an operating system, and then the CPU will succeed because now the page is in memory and it can be accessed. So this continuous execution is very important and happens on modern systems all the time as they page out data on disk, but it's something that for just an application developer, not an operating system developer, is kind of pointless. As said, it's not likely that you would find yourself in a situation where you could tell the code to resume and that would be somehow reasonable. And with C++, this will become even more unreasonable, so to say. And kind of course, C++ is a level of complexity just added on top of existing mechanisms. Okay, so let's try this. Let's run it. What happens? And as we see, so we enter test, then we are directly inside this exception handler. So we entered this, we did that, then this happened, and we never reached this code here. Like as soon as an exception happens, we bug out, and this can happen across, as you see here, multiple levels of function calls. So you can have like a function which calls a function which calls a function, and if the function bugs out, it will start the search upwards, and the first exception handler that feels responsible will then handle this. So here we can also put a breakpoint and step through the whole code just to see this in more detail. So we have here our call. We have a jump table which we don't care. Let me quickly clean up the thing a bit. So properties, linker, incremental linking, no. C++ general support just my code, no. Code generation, basic runtime checks, none. Security checks, none. Good enough. That should be that should yield a much cleaner assembly. So we go in here. We prepare a few things. We print it. We are not interested in the print implementation. Then we do our divide by 0. We go there. We do something. We step. Let's see. Okay, this will be the division, integer division. Zack. And bam, we are instantly here inside this exception handler. There is nothing that our application would see kind of that is in between, because basically what happens is the opcode is executed, the CPU sets an exception state and triggers an interrupt for the operating system to handle. The operating system then sees what's wrong, and in this case it sees, aha, okay, an exception happened, it's not a page fault, so it's nothing for me to handle. And then it would look up in the program whether there is a except handler registered for somewhere on the stack, and if there is, then it will update the instruction pointer to point to the right part of code. In this case, it would first go in here, so we can make this a bit more complex just in a second, and then it would execute the next thing. So like from our thread's perspective, we have a instruction pointer pointing to an instruction which causes an exception, then we wake up, and our pointer is our instruction pointer now points to some handling code, and a lot of things happened, but they happened outside of our perception, so to say, by the operating system. So let's add make this a bit more complex. Let's add a int filter 1, let's call this 1. And this needs to have the right types to work correctly. Unsigned integer code and underscore unsigned int code and exception. So this is a structure which the operating system will populate for us with various informations about what happened. So the instruction pointer where the exception happened, what sort of exception, some flags, etc., etc. So in principle, we could of course use this information to make some sort of educated decision what we want to do next. But of course, normally there is not much for us to do. But well, so let's continue. So we are here inside, yeah, inside filter 1, comma code %d or other %u, comma code. We will just print the exception code. We will not care for the other things, and then we return our exception handle, and then we'll pass this here, but we need to get the two information. So get exception code and get exception information. And those things, it's important to know, they are defined here in this except age, and they are a kind of already somewhat not just part of just C, but rather part of your current runtime and operating system. So you might find situations where you the accept and try and accept that should work on any platform, but for example, which functions you actually have to call to get additional information about the exception which you are just in process of handling, that might be platform specific. Okay. Right, so we have this, let's run it without breakpoint just to see here. So we see we enter the test function, we do the exception, then we enter the exception handler, we see what exception happened, and then we end up here. And if we would say not handle exception but continue search, then the operating system, as already mentioned, would be looking for another handler. So we can quickly demonstrate this by just creating yet another exception handler that will do that will filter and only react to certain exceptions, for example. So let's complicate these things a little bit more. So we are here inside. Let's move this further. Oops. Let's move this here. Okay, then we have our test function. We will put another handler into our test function. We will catch this with our test function. We call this filter 2. Inside exception filter in test. Filter 2 doesn't exist, so we need to make it. Filter 2. And here we will use continue search. Inside exception filter 2. Okay, let's run it. So as you see, we enter test. Test does the error. The error is caught by filter 2. Filter 2 enters here and decides continue search, so it does not, this we never reach. Then we get filter 1. Filter 1 decides I want to handle it, and then we go get this handler here. Of course, the handler could be empty. It would just kind of mean ignore it. Realistically, you would not have an empty handler. You would have something like then return error or something like that, so that you break out of this execution in some defined way. Any questions so far? Okay. If there are no questions, then let's keep and complicate things a little bit more. First of all, we'll add another bug. Let's say the reference null too long ptr null, oops, and type null ptr. So we want to have a different error so that we can do something funny. Int x equals null, and then say just asterisk x is equals 1. You can remember the code here. We had like, well, whatever this number is, and then if we try another exception, then we will in this case we say continue. So the order of operations is the operating system checks, is it a page fault, then is a debugger attached, and does the debugger want to handle these exceptions with a priority, in which case it then invokes the debugger instantly. We don't want, so we go to exception handling and just turn off everything so that our debugger will not get to see this exception, that instead the program has to handle it itself. And now when we run it, we see that we get a slightly different code and our debugger is not being involved. So this is what we want. And then what we could do, for example, we could implement it such that alright, let's run it again. Remember the thing, remember the number, and inside 2 if code equals this, then this, else, or well, we don't need else, or the other way around. If this is this, then this, and else continue execution. So now with this exception, we enter test, we enter our thingy. The thingy tells us our filter, I mean, the filter tells us that we should handle it, so the handler in test is executed, and then test exits as it should, gracefully. If we, however, cause the other error, the filter 2 says, nope, I'm not responsible, and then filter 1 says, well, I take everything, and then we end up in the exception handler in main. And of course, if we would not have an exception handler in main, then we would still get a, oh wait, that was wrong. I commented out the wrong function here. Then we would still end up with the compiler, the debugger being invoked. So before crashing the application, even if we say we are not interested in the exceptions, if the exception goes to top level without being handled, then the debugger, if one is attached, will be invoked. Of course, if we wouldn't have a debugger, then Windows would just create a crash dump or not, but log an application crash and kill the process automatically. Right, so as much for this. And one more thing about the C side of exception handling, there is also a second mechanism which is worth knowing. It's not quite not quite related to exceptions, but also quite useful. Try. Finally. This thing doesn't take any argument, doesn't do anything here. The idea is that when you have a code block that runs, there are different ways how you can exit the code block. You can of course crash an exception, but you could also, for example, call return or something. And the idea is that with a finally, you can define what will be done once we exit the code block, no matter how we are exiting it. So finally, inside, well, finally in main, And let's do the same thing to our thing here. We have some indentations misaligned inside finally in test. Okay, suck. And we see, so we arrive in both exception filters, and then we arrive here in both finally cases, and then but still, as you see, we did not had this entry test, so this entry exit. So we enter the test function, we got our exception here, then we got the exception handler, which in this case does nothing, then we get the other exception handler, and when the exception handlers are done, then the finally things are being executed one after the other. So this one here first, and then the other one here. So this way we would be able to somehow clean up still something if we would want to. And then of course the thing is crashed. So that's it. We can of course add maybe here one few more things. Enter main and exit main. And let's put a breakpoint here and here because this is interesting. Or maybe even a few more. Right, let's also switch this to the other example that handles everything and see the order of operations. So we enter main, we enter test. Test does something that it shouldn't, it creates a crash. Then we enter here the exception filter for test, so this thing here, exception filter 2, and the exception filter tells us what is supposed to happen next. Then we get the finally block executed, so this thing. Then we get into the exception, and only then after this the exception filter here gets executed. And oops, and then we get to exit test because we already caught this, and then even though we exited gracefully, we still do the exception, the finally for here. So this is not dependent on having an exception, it always happens when you exit a code block, no matter how. And then we of course then exit main, and this part of code has not been touched. And we switch again to our other exception and see how this behaves. We see here, so we enter main, we enter test, then we have exception filter 2 which says it's not responsible, then we have exception filter 1 which says okay, I will handle it. But then before we enter this code here, first the finally in main, the finally in test is being executed, then the finally in main, and only then we get our exception handler to run. So that's how this works. We can also see if the order here makes any difference. So if we switch exception with finally, this will change anything. And as you see here, it does. Now we do the exception handler in main first, and then only once we're done we do the finally. The more interesting test case is of course how this behaves if we swap this to here. Okay, run. And we see here that in this case that doesn't change anything. So we have main, we have test, we have filter 1, filter 2, finally in test, then exception handler in main as before. The finally were first, and only the outer finally is then last, as we see here, since in this case we do not have an exception to mess up our order of operations. Okay, and this will pretty much be it. let's see if there is anything important. Yeah, there is one thing that I can also show you. Inside this finally statement, we can find out if this finally is invoked normally or because of some sort of issue. So here, let's add procent %s so that we print a additional string, comma, abnormal, didn't work, abnormal termination, question mark, L, let's print abnormal, and then we'll just print normal, and then we of course do the same thing to this thing here, in test, and let's run it again. Wait, that should be capital S. Or we just don't do L. I mixed here wide strings with narrow strings. That was not elegant. Right, and in this case, as you see, both say abnormal, and of course, if here we change this order, the finally is outside the handler, then the order of course changed, and then the internal says abnormal, but the outer says normal because the exception handler was executed here first in its entirety. Okay, and now we are already almost out of time, so let's quickly see how those mechanisms work with C++. So we can comment this out, or let's leave it. Let's just rename main to underscore main so it doesn't trigger. Int main. Oops, that was already int. And let's do the C++ case. In C++. So in C++ it is similar with regard to the syntax, but the behavior is quite significantly different. So first of all, you just write try without the underscores, and then to catch an exception, write catch. And the catch here expects an argument, but it's completely different. So you can either use 3 dots, basically catch all, catch whatever, or you can also catch something specific, like for example int. And this is quite interesting that you have here types. We'll see how this works in a second. So let's make a function that does something wrong. Void myfunc. And here what you would want is you would not longer well, simulate, or in this case really do something wrong. You could just throw an exception as you want. You would use the keyword throw, and you can just throw a value, and this will then be here handled as an exception. And it doesn't not simply have to be an integer, it can be really anything. So here printf code n unknown \n code n int exception %e comma e error, and when we run it it will then print us this 1, 2, 3 code. So you can of course test how this behaves if we actually cause a real exception. When I click, let's just get to our divide by 0. Instead of throwing knowingly and purposefully an exception, we will just oops, it's missing a semicolon. Divide by 0 here. And as you see, we have ended up in our divide by 0 debugger catch. So the C++ exception handling completely ignored our C exception, which we have had triggered here. So those exception handling mechanisms are quite independent. We can see if the system will handle it correctly if we try to nest this. Zack. And as you see here, the compiler does not want to allow us to mix try and except blocks. But what of course would work is to just a normal catch, and if you really would want to catch both sorts of exceptions, then you would need to use some sort of function based isolation between those two mechanisms. Let's call my test func. So we can do it like this. So first we catch C exceptions. No, other way around. First we catch C++ exceptions, and then we get C exceptions. So in this case, filter 1, handle in main, suck. And if we want to throw something, then caught an integer exception. So I'll just let to avoid typos. So you can use both mechanisms at the same time, but it's generally discouraged, and you need to explicitly separate them into independent functions. So here, since we are now just doing the C part, let's just stick to our throwing. And the nice thing is that when you're throwing something, we could also just throw a string. Exclamation mark. Then we can just make another catch statement. Catch char, const char, const. One sometimes needs to be a bit careful, like what we are catching. If you are catching const or const char, it might not necessarily always do what you want. %s, and this should be s error. Right, so const char is the right thing to catch, and here bam error. And if you would be let's see how tolerant this is. If we just catch char, not const char, as you see, we fall into the unknown exception. So you need to be a bit careful here what you are catching. The system is a bit restrictive. You cannot here then kind of determine what you didn't caught. You just know that this is an unknown exception, and that's it, so to say. But of course, not just integer and strings can be thrown. You can throw anything, literally anything. We can create our own struct. My exception. We can edit a constant. Let's go with class. Let's go all in. Class as my my class. Needs to be of course public. My exception int code const char error. Error, let's say, is optional. Then we need a destructor. And then we have a int code that's private, and char asterisk let's call this message msq message. That's also null. In the destructor we delete message msq. And here we set code is equals code, and if message, then message is equals new char n plus 1 comma. Okay, and then we need the function to then the function int get code code and get const char asterisk get msq return msq, and then we can throw my exception 1, 2, 3. Zack. And then we of course need a catcher for that. My exception. My exception error. Exception, comma, code, synchronous. Okay, so code is E, message is S. Punkt get code, comma, punkt get message. Okay, let's run. We broke something. Our destructor was not happy. What did we do wrong here? Copy string jar string +1 of message. That should be fine. Did we print anything to the console? Let's see what we printed to the console. So this worked. We just crashed in the we're just oh wait, okay, delete is correct. That should be fine. Let's step through it step by step. So then we go into new. Call new. Step size 10. That sounds correct. Is this when we step out of this? Is this 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, and the 0, that is correct. And then we string copy this into that, and we can just add a few more bytes in case we get some memory corruption. Oh, it's something other that it doesn't like. It says invalid address. Why wouldn't it like the address? Let's run it again. Is the memory correct? The content is correct. Your get message should be also fine. Let's quickly see if this is somehow related. Oops. 0 is 0. Like that. Why would this? Oh, I know why. Because we go by make a copy. We run into the default copy constructor. We need to do this by reference here. Now it will be fine. So basically we created my exception, and when we entered this part of the code, we made a new my exception is equals the old one, which caused the two pointers to refer to a message. Now it's fine. And then of course we had the destructor being called twice, and then of course one succeeded and the other one didn't. Our smart pointer, if we would have used it for char asterisk, would have saved us here. Right, so as you see, this is quite complex and quite convenient, but it's not yet the most impressive thing about it, because what's more important is that if we create objects, then when the exception happens, then they can still be uh, nicely deallocated. So let's quickly test this. So uh, my struct1 int val. Let's create a constructor and destructor for it, and print what happens. So f x/n. Do the same for the destructor. Okay, so we create our mystruct1. Should be as mystruct1, then we can use mystruct1 for the variable name. Okay, so we create a structure, and then we will be running into an exception. And as you see here, we get the exception handler, and then still the destructor for the structure has been called, even though in principle no code after my func should be executed. So we can here before exception, after exception. And as you remember, normally when here we close the scope, we can put this in an extra scope. Then here on the end of the thing, normally the destruction happens, and here we see that we create a structure. We are before exception. I forgot the backslash n, that makes it ugly. Now it's fine. Okay, let's rerun it now with a new line. So we create our structure. We are before the exception. Then the exception happens. Actually, we should add a log before. Actually, we can be fancy. We can go into our exception and say exception exclamation marks. So we are before exception. We have the exception, and then the destructor still gets executed for our structure, and only after this is done, our error handling here is invoked. So this C++ type of structured exception handling, or rather way of structured exception handling, does not allow us to tell it to continue, because at this point it knows that things have been torn down. But you can also kind of see that basically at the end here, what happens, all the destructors are called by a mechanism as is used for this finally. It follows the same order in a way as did the other thing. While we enter the filter first before finally, we enter the exception handler the exception handler only after finally. And here in C++ it happens similarly. The finally destroys everything, no matter whether we ended the scope gracefully or we aborted somehow, and then only our exception handler is executed. So you can also kind of see that those mechanisms are internally related and built one on top of the other. But it's something that for us is quite opaque. We don't have that much access to the internals of how this is implemented, and every operating system implements it in its own way. So it's not like being somehow easily generalizable. Although, of course, given that it runs on the same CPUs, the methods the operating system authors would have to choose will need to be sufficiently similar. So here we don't need this scope. We can also put a breakpoint into this to see from where we come. and we see here that so we had here my function, and we threw the exception, and then let's load a few symbols here. Load symbols, and okay, that will need a second. And for this one, load symbols, and for this one, load symbols. That should be all we need. Wait, this one as well, load symbols. So basically, our throw keyword internally is implemented by calling the _cxx throw exception function, which contains a exception object plus some throw informations. This thing then will prepare some semi-documented data and feed this to the raise exception, which then calls another exception handler on the TDLL, which then keeps processing the thing like dispatch exception, etc., unwind, etc. And at some point, the internal mechanisms will come back to our destructor and invoke it. And once those things have been executed, we'll put another breakpoint here. Still from our now we will end up in our frame exception handler, which will then here do the printing. So we can quickly switch back to our just C mechanism and observe how there those things happen. So we want to see the finally and this and this and this. Zack. Do we have two mains? Yeah, this one needs to return something. Oops. Typo. Right. So here, as you see, in the finally, we have a C specific handle. So it's a different internal mechanism, but some functions like here this exception dispatch, etc., are reused. So here obviously you see it is much simpler, but it's obvious that some parts of the mechanism are shared amongst those both exception handling mechanisms. Okay, let's go back to our C thing. We can of course also have a structure, another one here. Then let's make this one the struct 1. Sorry, the struct 2. Oh no, let's keep this one 1 and the other one will be 2. This one will be then 2. 2, zack, 2, 2, 2, 2, 2. And then we here just copy main. Then we have here our, and we wanted struct 2. Let's run. I forget. Yeah, this one. I think there is another typo somewhere. This was all. We don't need a breakpoint. This is not interesting. We just want to see the thing here. And as you can see here, we create one thing, we are before the exception, then we create the other thing, we are still before the exception, and we do the exception, then both destructors are executed, and only once these are done, then the exception handler is invoked. So, and here, even if you would have more functions inside functions, each of them creating such structures and doing something with them, or classes, doesn't matter, objects, that's the important thing. Once somewhere inside the whole thing you trigger a throw, and then the whole stack will be unrolled, and the destructors for all the objects that have been created on the stack will be invoked. And this is quite powerful, because this means that if we create our smart pointer and are using our smart pointer or another smart pointer, and then we say throw, we don't need to care whether there are some smart pointers which are pointing yet to something, because they will all get their destructors called gracefully and will be properly deallocated. With just C, it's obvious that if the function here our test function would be allocating some memory. Um, if it crashes, then basically you would need to, for example, put everything in try finally statements to ensure that the resources will be freed. So it is much more complicated to properly handle errors, exceptions in C, because if you really want to make your function such that it can crash, and you don't expect this to just, okay, if this crashes then the whole application crashes, but you want it somehow to, this can crash and the application should continue, then every function that you are calling, inside it you need to make sure that any memory which is allocated will be freed by such a finally statement before the function exits, even if it crashes somewhere in the middle. So this requires significant discipline to program things in the correct way. Plus, you are limited with regard to which functions you can call, because if you are using functions from libraries, which are just C libraries, you might not know how they're handled internally. You could of course assume that if you have a crash, then it's in your code and not in one of the library functions, when in which case it would be fine. But if you would have a crash in a library function which does not clean up memory correctly, then you would still end up with a memory leak, so that would not be good. Using C++ and C++'s structured exception handling kind of does all of that for you. You just create your try catch and then some of your exceptions, and you can throw an exception if something happens you don't like at any time, and you don't need to care for all the other things getting deallocated, under only the one assumption that inside of your code you are always using smart pointers, and as I said earlier, you should do that always anyways. So just using raw pointers in modern C++ is not really recommended. Of course, if you are optimizing something and have some small piece of hot code which needs this for performance, you can do it, but this is like the exception, the optimization case, and it should not be the default case. Yeah, what else? You can of course use such smart pointers, especially if they have a custom deleter, not just for allocating memory, but for example when you are opening a file, Windows will create a handle object for your process, and this handle object, if you accumulate too many in your process, this will also not be good. You could cause problems for the whole system. Now with modern systems, the handle limits are so high that you probably will crash before that, but on older systems you could exhaust the amount of available file handles and then the whole operating system would crash. That would not be great. So using here such a smart pointer to hold the handle and then properly call the appropriate close function for it would also help you with such issues. So this is simply put generally a very powerful programming pattern. You can use this also. You could put more code into your Lambda to add some other cleanup. Really, it's mostly limited by your imagination. You can do very many things with this, and generally, as said, you should use such smart pointers. With regard to these exceptions, what for example you could do with them is when you create a smart pointer with your square bracket operator, this operator is supposed to return a entry by reference. So you cannot bug out from there without raising an exception. And this would, for example, be the ideal case to use our exception. So in the next lecture, we will be implementing a simple, either just a simple list or a simple array type of object, and use the exception mechanism to throw exceptions if someone tries to access something that they shouldn't. Yeah, any questions? Okay, if there are no questions, then just for completeness, the alternative pattern to using exceptions is to use return values. So basically you have a function that does something, and either it succeeds or it returns you an error code, and you know something went wrong. In case of some types of functions like the square bracket operator, you cannot do this, because if you would return null as to indicate an error, the code generator that uses your square bracket operator would of course then try a null object access, and then it would cause a CPU exception, so that wouldn't be good. But for most other use cases, you could have, for example, a function get reference at, which takes a pointer which it will populate um, with the right value, pointing to the entry inside of your table and the index, and then it returns true on success or false on failure. So you can write perfectly fine C code completely without using any exceptions. Um, and often this is also preferred because it's more efficient. So the exception handling mechanism is good, but it is much more CPU intensive because it invokes the operating system's error handling and a lot of stack unrolling. So if you want your code to be as optimal as possible, you should use exceptions. Usually just in such cases where something very exceptional happens and then you really want to bug out and you don't maybe want to make every function having a dedicated return error code and then check this error code and so on and so on. So with this error code, of course, it's more the standard C way of doing things, because then after every function call you need to check this error code, which means you need to type more code yourself. So it's not convenient. Just throwing an exception takes care of all of that, works automagically, so to say, which is quite nice. But as said, it's not performance. So um, in situations where you know that you will often return an exception, or rather often want to return an error, you should just use an error value instead of using exceptions. What you also can do is you can mix, of course, both mechanisms. You can have your exceptions for the exceptional critical things that should never happen, or at least very rarely, and for those things that can happen often but still mandate some sort of abortive operation, you could just use the return value. And since we are running out of time, um, today there will be no homework, I think, or maybe can I come up with something? Not really. There will be enough homework during the next lecture. If you have any questions, you can email them to me at any time. And we are also only have, I think, 4 lectures left. So at the beginning of next month, I will assign the final project. So you all should be there to ask if you have any questions about the final project. And for the final project, you will have until the end of the semester to complete that. Yeah. Any questions? Okay. Still no questions. Then let's finish for today. Stop recording.